To Lecture 9, Energy and Emissions. So in this lecture, we will be talking about greenhouse gas emissions. We will be discussing where they come from in the U.S., what are the sources of greenhouse gas emissions, and what different greenhouse gases the emissions are composed of, and percentages. We'll be looking at percentages. For example, what percentage of greenhouse gas emissions comes from electricity generation? What percentage of greenhouse gas emissions, again, this is for the U.S., we'll be focusing mainly on, comes from carbon dioxide? And we'll be talking about the sources to make electricity. Okay, how do we make electricity? Where does the electricity have the lights on at your home, or your phone plugged into charge? Where does that electricity come from? We will be discussing light bulbs and talking about how incandescent light bulbs are being phased out, and compact fluorescent light bulbs are starting to replace them, along with LED bulbs. And we'll be talking about the advantages of compact fluorescent, or CFL, light bulbs over incandescent light bulbs. We'll be talking about energy, and there's a couple types of energy when we talk about in terms of using it at home, or using it to make and use products. There's indirect and direct energy. And then we'll finish the lecture talking about mitigation, ways to help address the issue of global warming from the energy usage. So how is energy related to global warming? Well, for decades, the energy generation in the United States has primarily relied on the burning of fossil fuels. And recall that there are three major fossil fuels: coal, crude oil, also known as petroleum, and natural gas. And fossil fuel is basically a general term for buried combustible or burnable geologic deposits of organic materials formed from decayed plants and animals that have been converted into crude oil, coal, or natural gas by exposure to intense heat and pressure in the Earth's crust over hundreds of millions of years. So basically, fossil fuels form from which decayed organic material gets converted into these substances over that we can use to generate energy over very long time periods, hundreds of millions of years. And when you burn fossil fuels, that emits greenhouse gases into the atmosphere, okay? And that hence plays a role in climate change. So in order to generate energy, to have the lights on at your home, to use products, to make goods, it takes fossil fuel burning, okay? And so one way to mitigate against the effects of global warming is to burn less fossil fuels, use less energy, right? And in the coming decades, it is not only important to reduce energy usage, to help reduce the burning of fossil fuels and reduce emissions of greenhouse gases, but also look into alternative energy sources for transportation, as well as alternative energy sources for electricity generation. Because it turns out that most of the energy from transportation and power generation comes from fossil fuel burning, and these fossil fuels are not renewable resources. There is a finite supply of fossil fuels, and so not only when we burn them that contributes to global warming, But as we continue to burn them, we reduce our remaining supply. So eventually we have to turn to alternative energy sources because these fossil fuels are not infinite. So, let's talk about where U.S. greenhouse gas emissions come from. So here are the different sources of greenhouse gas emissions in the U.S. for 2012. So this is this data is a few years old, but it's the values are very close today still. And so what do you see? What is the largest source of greenhouse gas emissions in the U.S.? It is electricity generation. So about a third of all greenhouse gas emissions in the U.S. comes to make electricity. Okay, to again have the lights on at home, have the computers on at school, have the TVs on in the Target electronics section, right? So that electricity generation is responsible for about a third of greenhouse gas emissions here in the United States. And then the second largest source of greenhouse gas emissions in the U.S. is transportation. So this includes the emissions from driving your car, from taking the bus, from flying in airplanes, okay, the emissions from tractor trailers that are used to transport goods across the U.S., right? The third largest source of greenhouse gas emissions in the U.S. is industry. What do you think industry is? Well, that's basically manufacturing and factories, okay? So the greenhouse gas emissions that are released, the greenhouse gases that are released when you burn oil to make plastic, okay? And you burn these fossil fuels to make goods, okay? We have commercial and residential usage, which makes up 10% of U.S. greenhouse gas emissions. That includes the burning of coal or natural gas to heat the home, the disposal of waste at home, use of certain products that have greenhouse gases, and about 10% of U.S. greenhouse gas emissions come from agriculture. That includes livestock on farms like cows. That includes production of rice. That includes pesticide use, okay, fertilization. So hopefully you now have a good understanding of the different sources of greenhouse gas emissions in the U.S. And by the way, for transportation, the overwhelming majority of energy for transportation comes from petroleum, okay, crude oil. So, now let's talk about the specific greenhouse gases that make up the emissions for 2012. And you've seen a similar figure before. You saw a figure that was a few years older than this one, but the values were pretty similar, right? So what do you see? You see that over 4/5, 82% of all greenhouse gas emissions in the U.S. are from carbon dioxide, okay, CO2. There's a reason where you have talked about it so much, okay? 9% of U.S. greenhouse gas emissions are from methane, CH4. 6% of U.S. greenhouse gas emissions are from nitrous oxide. And 3% of U.S. greenhouse gas emissions are fluorinated gases. Okay, so carbon dioxide sources include burning of coal and natural gas to generate power, burning of products like gasoline and diesel made from oil to have energy for transportation, manufacturing goods. Okay, methane emissions include those from livestock. Include what's released from landfills, extraction and burning of natural gas. Turns out natural gas is mostly made up of methane. Recall that nitrous oxide is laughing gas, and the primary source of nitrous oxide emissions is for agricultural purposes, specifically for irrigation, fertilization, and pesticide use on crops. By the way, these fluorinated gases are a way to revert to alt change. They're basically a substitute for the CFCs that were being released and causing depletion of the ozone layer. So, by the way, if you add up all the emissions of these individual greenhouse gases, you'd see that there are 6,526 million metric tons of carbon dioxide emitted for this year, 2012. Okay, so now that we know that the largest source of emissions in the U.S. is electricity generation, and by the way, that applies to the world as well, let's determine how we generate the electricity. Because obviously, if that is the largest source of greenhouse gas emissions in the world, as well as in the U.S., that kind of has the greatest potential. That source has the altering how we generate electricity has the largest potential to reduce emissions, right? Because that's our largest source of greenhouse gas emissions, right? Makes sense. We have a lot of potential to do good if we can change how we make electricity. So how is electricity generated? Here are the different sources of electricity generation in the U.S. as of 2013. What's the largest source of electricity generation? It's coal, 39%, as you see here. Okay, 39%. The second largest source of electricity generation in the U.S. is natural gas, and that makes up about a little more than a quarter, 27% of the U.S.'s power is made from burning of natural gas, okay, natural gas power plants. And when you have coal power plants and natural gas power plants, they both emit carbon dioxide. Natural gas also emits, burning of the natural gas power plants also emit methane. They both emit aerosols as well. Although natural gas burning is cleaner than coal burning, it emits less greenhouse gases. It also releases fewer aerosols, so it is better for air quality. And by the way, in recent years, a lot of the new electricity capacity in the U.S. has come from natural gas. And it turns out now, if you looked at the current data, now natural gas, there's almost as much electricity made from natural gas as coal in the U.S. So natural gas was the share of electricity from natural gas was rising in the 2000s and then into the 2010s, and now about as much electricity is made from natural gas as coal in the U.S. Okay, 19% of electricity in the U.S. is generated from nuclear power. We'll be talking about that in lecture 11 when we talk about alternative sources for electricity generation. Okay, lecture 12. 7% of U.S. greenhouse gas U.S. electricity was made from hydroelectric. What do you think hydroelectric refers to? Dams, basically. Okay, dams that are used to generate electricity from moving water. And then you see some of these smaller percentages showing renewable sources. Example, biomass. Okay, making electricity actually from oil, from different oils that are produced from living material. You might have heard of ethanol and biofuels for transportation. You also can generate electricity from biofuels to you can also generate energy for electricity, not just transportation for biofuels. Geothermal is the generates electricity. It generates electricity from underground heat. It turns out as you go deeper underground, closer to the center of the Earth, it gets hotter. And you can actually make electricity using the heat from the planet's interior. This is especially done in Northern California. Especially far Northern California and the Northern California coast along 101. Solar was responsible for 0.23% of U.S. electricity generation in 2013. Yes, it doesn't sound like much, but it's rising. Now it's up to around 1%. And yeah, just in the past few years, there's been a tremendous increase in the amount of electricity generated from solar. And also solar has become much less expensive. The prices are quickly dropping as the technology improves and the panels become longer lasting. And this is great news because now solar is starting to become affordable for many people. 4.13% of U.S. electricity was generated from wind. So you've probably seen wind turbines before. There's a few large wind farms in the Bay Area. There's the Altamont Pass wind farm with nearly 5,000 turbines. You see that if you drive over 580 past Livermore into the Central Valley. There's also a wind farm north of the Delta, just beyond the Antioch area. Okay, so you may have seen that driving along Highway 4 along the Delta. And there are other wind farms. 1% of electricity was generated from petroleum or crude oil. So while oil is the dominant energy source for transportation, very little electricity is generated from it. And then we have some other gases as well. Okay, so I'll have another slide here that lays out some of the major conclusions from this figure and some of the major points that I want you to understand. Okay, so here they are. I want you to know that in 2013, the largest energy sources for power generation in our country were coal, which was responsible for 39% of U.S. electricity making. Natural gas was the second largest energy source at 27%, and nuclear was the third largest energy source at 19%. We will be talking more about nuclear in the future. It's interesting because in a way nuclear is a clean source of energy. Nuclear power plants do not emit aerosols or greenhouse gases, but because of the very small but real danger of nuclear power plants of meltdowns and reactor explosions, some of the public is uneasy about nuclear power. Okay. Now, fossil fuels make up 2/3 of power generation. So remember the fossil fuels, the three fossil fuels, coal, oil, natural gas. If you added up the relative contributions of electricity generation from the fossil fuels, you'd see that 2/3 of the U.S.'s power comes from fossil fuels. Okay. So again, most of the electricity that's made in the U.S. comes from fossil fuels. But renewable resources now make up 13.25% of U.S. electricity generation. And by the way, this is up from 10% in 2006. So in recent years, the relative share of renewable sources to total power generation in the U.S. has increased. Now, as of 2016, it's nearly 15%. So this is really good news. We're starting to see more of our electricity made from clean sources that can be naturally replenished over time. Okay, there's many benefits of renewable sources. Not only can they be replenished, and unlike fossil fuels, they are not finite in supply. They have the potential to last for centuries to millennia, but they also are cleaner. They do not emit greenhouse gases, generally, unlike fossil fuels. Okay, what about California? We know California, the most populous state in the Union, with around 40 million people now. We know California is the Golden State. Okay, that's the nickname, right? And it's also the Green State. California is a very environmental state. And one way you can see that is when you look at the sources of electricity generation in California. So in California, when you start looking at how we generate our power, you'll see that we get more of the electricity from renewable sources. So first of all, you see the largest source of electricity generation in California is natural gas, 44.31%. And that's much different from the U.S. as a whole. Remember, in the U.S., at least as of 2013, it's changed a little to now, but as of 2013, the largest energy source, or largest source of electricity generation in the U.S. was coal. California, it's natural gas. Yes, natural gas is still a fossil fuel, but it's cleaner fossil fuel. Okay, natural gas power plants emit a lot less pollution, aerosols, and fewer greenhouse gases to generate the same amount of electricity as coal power plants. And then what you'll see again when you look at these renewable sources, look at the numbers, and think back to when you were looking at the renewable sources used to generate electricity in the U.S. as a whole. The numbers are larger. For example, in the U.S., 7% of the electricity was from hydroelectric. California, it's 9%. In the U.S., about 0.23% of the power was made from solar. In California, it's nearly 2%. And today, it's actually gotten to around 5%. Close to nearly 5% of California's power is made from solar, mainly solar panels, which you see on houses. You're seeing them more and more, right, in recent years. And in the U.S., about 4% of electricity came from wind in 2013. In California, it's about 8.55%. And today it might be 10%. Okay. Only 7.82% of California's electricity generated in 2013 was from coal. And that's much different from the U.S. as a whole, right? Basically, no electricity in California is made from petroleum. You see, unspecified is responsible for 12.49% of California's electricity making in 2013. And often I'll get asked in class about that. What's unspecified? Is it like a mystery gas? Is it like information the government's keeping from us? It's honestly, from my understanding, it's we're not exactly sure where 12.49% of the electricity generation is from in California, but it's likely from some of these other sources. Okay, so it's not like a special new way, a source that's not on here. It's a collection of these other sources that we know, but we're just not exactly sure of how much of each, if that makes sense. Okay, so don't worry too much about it. It's 12.49%. It's not too large of a number. Doesn't take away from how the largest source of electricity and generation in California is natural gas. Doesn't take away from the fact that we get significantly more electricity from each renewable source in California compared to the U.S. Okay, so a lot of information on this pie diagram, and here's kind of a summary slide illustrating some of the major points. Okay, so in 2013, the largest sources for power generation in California were natural gas, 44.31%. Second was hydroelectric, 9.05%. Okay, so nearly a tenth of California's power comes from dams. Third was nuclear at 8.84%. And fourth was wind, 8.55%. So recognize that two of the four largest sources of electricity generation in California are renewable, right? So that's good, right? And there's much less reliance on coal than for the U.S. as a whole. Whereas in 2013, the largest source of electricity generation in the U.S. was coal. In California, that was a fairly small source. 52% of power generation is from fossil fuels. So about half of California's electricity comes from fossil fuels. That's somewhat less than for the U.S. as a whole, where for the whole country, 2/3 of the power comes from fossil fuels. California, it's only about half. And here's great news. 27%, more than a quarter of California's electricity is generated from renewable sources. And that's up from 23% in 2008. So I think this really sounds good, right? Over a quarter of California's power comes from renewable sources such as hydroelectric, wind, solar, geothermal, tide wave. So this is great. And remember, California is the most populous state, and there's that saying, as California goes, so goes the nation, right? So if California can have such a significant amount of electricity generated from renewables, then why not the U.S. as a whole, right? Hopefully California can be a great example for the rest of the U.S. Okay. Some more information about natural gas, because we have been talking about it. It's mainly made up of methane, CH4, along with smaller amounts of other hydrocarbons. So generally about 70 to 90% of natural gas is methane. Smaller amounts of ethane, C2H6, propane, C3H8, and butane, C4H10, are in natural gas. So you might remember King of the Hill. Hank Hill sells propane and propane accessories. And Tom Anderson from Beavis and Butthead, who has some resemblance to Hank Hill, talks more about butane regulator. Okay. So natural gas, where does it come from? It can be extracted from a variety of places. Oil wells. Once the oil has been completely removed, there can be some natural gas in there that you can use. Also, once coal has been removed from the coal bed, there may be natural gas. There are also natural gas deposits underground. And landfills, basically dumps, emit natural gas too. They emit methane, and part of the reason they emit methane is because there is natural gas that decays, and natural gas is mainly made of methane. Natural gas burning is cleaner than burning of coal or petroleum. Okay? So there's a reason that more of the electricity recent new capacity for electricity generation in the U.S. has come from natural gas. It is cleaner than burning of coal for power. And then, by the way, when you burn natural gas instead of gasoline in a car or in a bus, that's going to be cleaner. Natural gas emits less greenhouse gases like carbon dioxide and nitrous oxide, and it releases fewer aerosols. So it makes for better air quality. Okay. But like coal and petroleum, it is a non-renewable resource, which means it has a limited supply. Natural gas cannot be naturally replenished over time. So recognize that natural gas might be a nice, in a way, a transition between coal for power generation, between oil for transportation energy, to renewables, but it's not the long-term answer. It's not going to save us in the future forever because we only have so much natural gas that we can extract from underground. And it's not completely clean. Even though it releases less greenhouse gases than coal or oil, it still releases them. By the way, here's some good information for the Green Ninja Project. What's natural gas used for at home? On the handout, you'll see that you are asked to track your electricity and natural gas usage at home. So we know what electricity is used for at home, right? To turn your TV on, to charge your phone, to make the coffee pot go on so you can turn up in the morning, okay? Get your day going right. Well, what do we use natural gas for at home? Mainly heating. Okay, mainly heating. Um, and there's three major um, reasons for the heating, or three major types of heating natural gas is used for at home. Okay, so pay attention to this. One, space heating. Some furnaces are powered by natural gas, so in the wintertime when it's cold, you might turn your heater on. That could be powered by natural gas. Two, cooking. There are both natural gas ovens and natural gas stoves. Okay, so you might have a natural gas oven. And a stove is usually part of the oven, right? But you might use natural gas to heat the oven up or heat the burner up. And finally, water heating is another way to use natural gas for heating. You might have a natural gas water heater, okay? So in order to make the temperature of the shower water nice and warm, right, you might use natural gas. Not all of you will use natural gas. If you go on your PG&E account online and you don't have the option to change the fuel type, if instead of saying select fuel type with an option to, with an arrow next to electricity, an option to change to natural gas, it only says electricity and there's no, it says fuel type electricity and there's no option to change it, then you probably only use electricity, and that's okay. Not everyone uses natural gas at home. Okay, so even though natural gas is cleaner burning than coal or petroleum, there are issues involving the extraction of natural gas. You might have heard of this. One way to extract natural gas is fracking. So most natural gas extraction today involves hydraulic fracturing or fracking. This is a technique to get the natural gas from underground that involves mixing chemicals with large quantities of water and sand and injecting that mixture into wells at high pressure. There are more than 500,000 active natural gas wells in the U.S. The role that natural gas fracking will play in the United States energy future is quickly evolving, okay? Like, for example, over the past 10 years, 81% of new electricity capacity has been gas-fired. And state governments are playing regulatory catch-up with this technology's rapid expansion to meet the growing demand. So there are issues with fracking, okay? Can you think of any of them? Yeah, like we said, U.S. is shifting towards electricity generated by natural gas. Well, one issue with natural gas fracking is that it can pollute the groundwater, and that may not be good for the underground ecosystems. Also, there is evidence that fracking can cause very small earthquakes. You may have heard in recent years, there's been a tremendous amount of very small and yet real earthquakes produced in Oklahoma because of all the fracking there. So it's kind of extraordinary that humans are actually causing ground movements because of all the the injection of the chemicals, water and sand mixture into the wells at very high pressure. It's actually causing the earth to respond. Most of these earthquakes can't be felt by humans. They can be detected by seismographs, and yet still it's somewhat scary, right? So fracking is an issue that needs to be addressed as the U.S. continues to generate a lot of its new electricity from natural gas. So, residential energy usage. Combined with commercial usage, usage in businesses, it makes up about 1/10 of greenhouse gas emissions in the U.S. And almost half of this sector's emissions are due to space heating and cooling. So if you're starting to wonder about what at your home uses a lot of energy, right? You're thinking about how to save energy, save money, do a good job on the Great Ninja Project. you might look first of all at changing the way you cool and heat your home. So let's look at what the different sources of household energy usage are. Here are the sources of household energy usage in the US, okay? For 1993, before a lot of you were probably born, maybe some of you were born, some of you were very young, and 2009. So, in 1993, what you see is that the largest source of energy consumption at home was space heating. Over more than half of all the energy used at home was to heat the home. 4.6% of household energy consumption in 1993 was from air conditioning. Doesn't sound like a lot. You might be used to thinking the air conditioner uses a lot of energy at home. And it can use a significant amount. But as you can see here in 93, a lot more was from space heating. 18.3% of the household energy usage in the US in 93 was from water heating. Okay. And 24%, about a quarter, was from appliances. Could be dishwasher, could be washer dryer for laundry, electronics, okay, computer, TV, right, VCR back then, right, lighting. And together, when you add up all these sources of energy consumption, you get about 10.01 quadrillion British thermal units total energy usage by all homes in the US in this year. Then what changed as we went to 2009, more recently? The total energy consumption in homes by end uses didn't change. This is for the average home. This isn't for all U.S. homes to combine. This is for the an average for each home. So the total energy usage of a home, it didn't change much. It increased slightly, very slightly. But what did change was the different sources and their relative contributions to total energy usage. So in 2009, yes, the largest source of energy usage at home was still space heating, but it was no longer more than a fifth. It was 41.5, more than half. It was 41.5%. And the second largest source of energy usage at home, appliances, electronics, and lighting greatly increased from slightly less than a quarter to more than a third. Okay, and why might this be? Well, maybe more people had computers, more people started getting larger TVs, right? You have to remember in 93, that was before the internet was around, and nobody had a computer in their house, and a significant amount of people still didn't have cable. So the relative contributions of water heating and air conditioning to total energy consumption at home did not change much from 93 to 2009. But the relative shares of space heating and appliances, electronics, and lighting did. Now, more about energy and power. And this will also be good information for the Green Ninja Project. Energy and power, how are they related? We might be used to think of them as kind of similar, right? It takes energy to have the lights on at home. It takes power to have the lights on at home. They're not exactly the same, but they are closely related. Energy is equal to power multiplied by time. Okay, it's a pretty simple equation, but it's a powerful equation. Think about this. Energy is equal to power multiplied by time. So the total energy something uses, whether it's an appliance, whether it's a light, whether it's an electronic device, the total energy it uses is equal to the power it takes to be on multiplied by the time it's on, right? So if something is not on at all, if time is 0, then there's no energy used, right? Because anything times 0 is 0. And if something is on for a certain amount of time, then the more power it takes to be on, the more energy is used. Okay? Now, power is measured in units of watts or kilowatts. And you may know that 1,000 watts is equal to 1 kilowatt. Okay? Kilo means 1,000. So, if you look at a computer, a TV, a light bulb, you'll be able to see how many watts the power is, right? And you take the power multiplied by time to see how much energy is used. On your PG&E bill, total energy usage is given in kilowatt hours, and 1 kilowatt hour is equal to 1 kilowatt multiplied by 1 hour. So power has units of watts or kilowatts. In this equation, energy equals power multiplied by time. Time is units of hours, and energy is measured in kilowatt hours. So if a device takes 1 kilowatt of power to be on and it's on for 1 hour, it would use 1 kilowatt hour of electricity. If it was on for 6 hours and it uses 1 kilowatt of power, it would use 6 kilowatt hours of electricity. And you'll develop more of an understanding of the relative amounts of kilowatt hours used at home in the coming slides. So, how does PG&E charge you money, and how do they decide how much money to charge you per amount of energy used? PG&E has what's called a tier system to determine rates. So generally, the more energy you use, the more money you have to pay per unit energy. Okay. So they have what's called a baseline. The baseline is basically the amount of energy intended to satisfy an average customer's electricity needs in a given area. Okay. So that depends on the area. It depends on say the neighborhood, how large the houses are, how many people live in each house, okay, the energy habits of a particular area. But generally the baseline is the maximum of energy that you should be using at your home. It should be enough to satisfy you. If you go beyond the baseline, you're basically using more energy than is needed to satisfy your needs. And then you start getting charged more per kilowatt hour of energy used. So, you see, up to the baseline period, PG&E charges 13 cents per kilowatt hour of energy used. These are rates from July of 2012. The rates are similar today. And these are basically average rates. If you qualify for reductions in rates, you might be low income, you might have used solar panels and qualify reductions in energy rates, you might pay less. Okay, so and depending on where you live, what part of the country you're in, what the energy usage is like where you are, will determine the actual rates. Okay. Then what happens is when you reach tier 2, when you start using 101 to 130% of the energy that you should be using in a monthly billing cycle, you get charged 15 cents per kilowatt hour. So generally PG&E has each billing period of about 30 days or a month. Okay, it might run from the beginning, the first of the month, to the 30th or 31st of the month. It might run from the 15th of one month to the 15th of the next month. Regardless, generally the billing period is about 30 days. And as long as you haven't yet exceeded the baseline period, or the baseline energy value or energy amount for that billing period, you get charged the baseline rate. Once you start to exceed the baseline amount, once you've used more total energy during the billing cycle than the baseline amount, you start getting charged more, 15 cents per kilowatt hour. for excess energy you're using. Okay? And as long as you don't go too high, you don't go more than 30% more energy usage than you should be at for the billing cycle, you don't get charged too much more. But then your rate really starts to go up if you start going beyond 30% more energy than you should be using. So when you are now at 131 to 200% of the baseline amount, okay, you're at between 31% more to twice as much energy as you should be using in a monthly billing cycle. Now you're paying 30 cents per kilowatt hour. And again, that's not saying you're now going to pay 30 cents for every kilowatt hour in the entire baseline period or entire monthly billing cycle. It's just once you start to exceed 30% more, once you now reach 131% of total baseline amount, then you start paying 30 cents per kilowatt hour for each, once you exceed, okay, 30% more, okay? And whether or not you exceed the baseline period, would depend on how much energy you use. Sometimes you might be at the baseline rate for 15 to 20 days of the 30-day billing cycle, and then beyond that, you might have to start paying more. When you get to Tier 4, you're at between 2 and 3 times as much energy as you should be using. Okay, so this is for electricity. Okay, you see kilowatt hours. This is for electricity. Let me be clear on that. It turns out that electricity is measured in kilowatt hours, but natural gas is measured in therms. So natural gas also has a tiering system, only 2 tiers. But when you see kilowatt hours, yes, it's a unit of energy, but when you see kilowatt hours on your PG&E bill, that's talking about your electricity usage, not your natural gas usage. If you're really an excess energy user, you're using now between 2 and 3 times as much energy you should be using. You're really starting to pay a lot per kilowatt hour, 34 cents per kilowatt hour. And Tier 5 is theoretically now when you're using more than 3 times as much energy as should satisfy your needs. You're still paying 34 cents per kilowatt hour, which is about 2.5 times the baseline rate. Okay. And here's another slide with information on tiers and pricing. The rates you see here are similar. They're not quite exactly the same, but they're similar. And here's some more information about the tiers. And by the way, natural gas uses a 2-tier system. So if you want, you can pause the video and review this slide. So let's provide some statistics on both American average daily electricity usage at home and daily average electricity usage at home for Santa Clara County, where many of you live. So 2012 average yearly electricity consumption by a residential customer in America was 10,837 kilowatt hours. So over the entire year, and that was a leap year, right? 366 days of that year, the average American residential customer used 10,837 kilowatt hours of electricity. Now, that number off the bat may not mean much, so if we divide that by the 366 days, we can find that the day, on average, each day an American residential customer uses 30 kilowatt hours of electricity. Okay, 30 kilowatt hours of electricity per day. And what about for Santa Clara County? In Santa Clara County, the daily average electricity usage at home is 18 kilowatt hours. And that is 40% less than for America as a whole. So you see that on average in Santa Clara County, we use significantly less electricity each day at home compared to the U.S. So that's interesting. And remember that natural gas usage is measured in therms. Some more information about average daily natural gas usage for Santa Clara County homes is provided in the Green Ninja Project handout. When you see residential customer here, that generally means for the entire home's account. So that doesn't mean if say 5 people live in a home, okay? That doesn't mean each person is using 30 kilowatt hours of electricity. That means the total home would be using 30 kilowatt hours of electricity. Generally, each home is only going to have one residential customer, right? Or one account, right? If you have roommates, there's probably just one account for your entire house. Okay, so that's what this daily average is referring to. The total energy usage at a home by one account. Okay. So let's talk about light bulbs. What do we have here? We have a couple pictures. On the left, we have an incandescent light bulb, and on the right, we have a compact fluorescent light bulb. Now, incandescent light bulbs are being phased out. They waste a lot of energy because they convert less than 5% of the energy they use into visible light. The remaining energy is converted into heat. Now, the incandescent light bulb works by incandescence, heat, which is the emission of light caused by heating the filament, a tungsten filament inside. It's heated up and produces light. Thomas Edison's often credited with the invention of the light bulb, the incandescent light bulb. There are a number of people who invented components and made significant discoveries regarding the light bulb. Now, incandescent light bulbs were quite popular during the 20th century for a variety of reasons. They don't require any external equipment to run or operate. They have a very low manufacturing cost. They work well with either alternating current or direct current. And they're compatible with control devices such as dimmers, timers, and photosensors. So, the incandescent light bulb is widely used in households and commercial lighting. But times are changing. The compact fluorescent light bulb on the right is a lighter lamp that's generally designed as a replacement for the incandescent bulb. And the one on the right is a screw-in. It's not a plug-in. There are two main types of the compact fluorescent light bulbs, the screw-in and the plug-ins. The screw-in compact fluorescent light bulbs don't require any external equipment. They can just be plugged right into where the incandescent light bulb was plugged in. So it's very easy to switch between the two. And compact fluorescent light bulbs are usually considered a fairly recent technology. The modern CFL was invented by Edward Hammer, an engineer at General Electric, but was not produced at the time due to high production costs, unlike is the case for incandescent bulbs. In 1980, Philips became the first manufacturer to mass produce a compact fluorescent light bulb with the screw-in base. Over the past 36 years, the technology has continued to improve. Today's CFL is smaller, produces more light per watt of power. It warms up more quickly, it has better quality of light, and it's much less expensive than CFLs from past years. How do they work? Well, CFL light bulbs use electricity emitted from cathodes inside to excite mercury vapor. And phosphors, which are solid materials that emit light, and a noble gas like argon are contained inside. And the mercury atoms that are exposed to electricity emitted from cathodes produce ultraviolet light. And the ultraviolet light causes the phosphors in the lamp to glow, producing visible light. There are some issues with CFLs. They're generally not well suited for use with control devices, such as dimmers, timers, or photosensors, although the recent ones are more compatible. As an example, a few years ago in my household, we replaced our dining room lights from incandescent to compact fluorescent, and we had a dimmer. But the new compact fluorescent light bulbs did not work well at the dimmer. So we can either have them off or at maximum capacity, but they don't. It's hard to turn the knob to dim them. And the newer CFL bulbs may be able to function okay with dimming or timing sensors, but this can reduce the life of them, and this type of usage may not be covered under manufacturer warranties. Okay. Despite these issues, there are a couple big advantages of CFL light bulbs over incandescent light bulbs. Okay. So most incandescent light bulbs are 40 to 100 watts. 40 watt, it's pretty dim, not bright enough for reading, whereas 100 watt is very bright. And CFL light bulbs, one, they use up to 75% less energy, and two, they last up to 10 times longer. Okay? So they can save you money in multiple ways because they use up to 75% less energy, so they save you money on your electricity bill each month. But they also last much longer, up to 10 times as long. So a incandescent light bulb might last a year or two, depending on how often you use it, right? And CFL light bulb might last 10, 20 years. And so that saves you money because you don't have to buy them as much. So even though it might be a little more upfront to buy the CFL light bulb compared to incandescent light bulb, although they've been coming down in price in recent years, you'll save money in the long run. Here's a diagram or figure illustrating how CFL light bulbs use less energy. So this shows basically the wattage required from a CFL bulb to produce the same light as an incandescent bulb. So for the 40 watt incandescent bulb, you only need a 10 watt CFL light bulb to produce the same luminescence. Okay, so that would use 75% less energy. A 75 watt incandescent light bulb is compatible to a 20 watt CFL light bulb. Okay, so that uses significantly less energy, right? And incandescent light bulbs are being phased out. In recent years, production of incandescent light bulbs in the U.S. has ceased. So as of January 2012, 100 watt incandescent light bulbs were no longer produced in America. As of January 2013, 75 watt incandescent light bulbs were no longer produced in America. And as of January 2014, 40 and 60 watt incandescent light bulbs are no longer produced. You can still buy incandescent light bulbs at stores like Target, Walmart. You can still buy them online, but they're no longer being produced. And once they run out, you won't be able to order them anymore. This includes both manufacturing in the U.S. and also import into the U.S. So not only are they no longer, the incandescent light bulbs are no longer being made in the U.S., but they're not being imported from other countries anymore. And this is to encourage people to switch over to CFL light bulbs, which are use less energy, they last longer, they save money, they help the environment. There are also LED light bulbs. Those also use less energy than incandescent light bulbs. You may have seen those. If you look at the book, chapter 9, there's some good information about the different types of replacement bulbs for incandescent. Okay. Let's talk about direct and indirect energy. What's the difference between direct and indirect energy? What do you think? A car, here's a Toyota, a red Toyota. Now, during its lifetime, from when it's made in the warehouse, right, in the factory, to when it's dead, when it decays, it emit 14 tons of greenhouse gases. And 86% of those emissions would be for direct energy, 14% were for indirect energy. Now, a computer might release 2.5 tons of greenhouse gases from birth to decay, and 83% of the emissions may be for indirect energy, and only 17% for direct energy. So what's the difference? Okay, what's the difference? Well, direct energy is basically the energy that is used when something is on. Okay, it's the energy used to drive the car or run the computer. Indirect energy is the energy required for the manufacture of the product, the transportation of the product from where it's made to where it's bought, the decay of the product. Okay, and so for the car, most of the energy that it will use over its lifetime is direct energy. It's the energy that it's using when it's being driven. Over 6 times as much direct energy as indirect energy. But for the computer, there's nearly 5 times as much indirect energy for it than direct energy. Most of the energy for the computer is to make all the goods, to assemble the products, okay, the coppers, the minerals, to ship the computer from where it's made to where it's bought, to get the computer from where it's bought to your home. So I have a nice example of indirect and direct energy for an Apple and an Apple iPod. And this iPod on the right is a second generation iPod. It's almost 10 years old. It was released on September 25th, 2006. The iPod Nano second generation. Okay, on the right, that's on the right. On the left, we have an Apple, and the Apple is listening to music. Now, both of these items have roughly the same size and weight. The Apple's a little heavier than the Apple iPod, but they're both pretty light, easy to hold. But the energy to produce and dispose of them is very different. Okay, let's start with the Apple. We can understand there's energy associated with growing the tree, including irrigation, watering, right, fertilization, and energy required to harvest and transport the apple to a nearby store or farmer's market. There's also the energy associated with disposing of the apple, right, after you've eaten it, unless you take every last bite. Let's take all this energy, add it up, and we'll have the total energy footprint of the apple. Let's call this 1 unit of energy. Okay, 1 energy unit. We can now do a similar calculation for the iPod, although this calculation is more involved. The analysis would start with the energy associated with the mining and production of various metals and minerals required for the electronics. Silicon, copper, aluminum. And then, after all the different pieces are made, you have to consider the energy to assemble the pieces together, to package it, right? When you order a new iPod, or when you buy it at the store, right, it's usually in a nice package. It's not just, naked, right? And then you have to consider the energy to transport it from where it's manufactured to a store near you. Often, products like electronics are made in China, okay, and it takes a lot of energy to transport the goods from China to U.S., right? You have to consider the energy to fly that thousands of miles across the Pacific Ocean. And then in this analysis, let's neglect the energy needed to power the product over its lifetime, the direct energy, which for these types of electrical devices is a very small percentage of the total energy, as you saw from the computer example. And don't worry too much about the energy needed to properly dispose. That's small as well. Based on results from previously published analyses of energy required for computer production, it can be estimated that
the production of an iPod requires how many energy units compared to the energy unit for the Apple? 100 to 500. This isn't too surprising because an iPod is quite a remarkable electronic achievement. Although so is the Apple, and it tastes better than the iPod. But it might be surprising for you to know that, at least for computers and other electronic devices, the energy required to manufacture and assemble the device is much greater, or perhaps 4 to 5 times as great as the energy required to operate the device over its lifetime. Okay, now moving on, talking about energy usage now for the transportation sector. Remember, transportation is the second largest source of greenhouse gas emissions in the U.S. Most of the energy for transportation comes from, or is derived from, oil. So here we're looking at fuel used for transportation in the U.S. in 2007. 62% of the fuel for transportation was gasoline, which of course is made from crude oil or petroleum. 22% of the fuel was diesel, diesel trucks, diesel engines and trucks and buses. 9% of the fuel was from jet fuel. 5% was other, and such as biofuels, and 2% was natural gas. And on the right you have the different vehicles and how much of the what share of total energy usage from the transportation sector they are responsible for. So for example, about a third, 32% of all energy usage in the transportation sector was from automobiles, cars, 28% was from light trucks, 16% was from other trucks like tractor trailers, 9% was aircraft, 5% was from water vessels like ships and boats, maybe submarines. 4% was from construction and agriculture vehicles like tractors to water crops, cranes, bulldozers. 3% was from pipelines. 3% was from trains and buses. Now, personal vehicles actually account for about 60% of the energy usage of the transportation sector, because automobiles and light trucks are both personal vehicles. Automobiles, they mean cars, but light trucks are also can be used for personal transportation or personal use. So what you see is that 60% of the energy usage in the transportation sector was from personal vehicles. Then if you remember that 28% of U.S. emissions in 2012 were from transportation, you can calculate that 17% of all greenhouse gas emissions in the U.S. in 2012 were from personal vehicles. Nearly a fifth. But that's significantly less than how many greenhouse gases are being emitted from power generation. So now, what are some reasons to reduce energy usage? We've been touching on some of them, but here are 5 important reasons to reduce energy usage in the future. 1, reduce the use of fossil fuels. Are fossil fuels renewable sources of energy? They're not. For example, if current oil usage rates continue, all of the world's petroleum will be used up within about 35 to 40 years. The fossil fuels, coal, oil, and natural gas, have finite lifetimes. They will not be around forever, so we have to eventually get away from them. And if we reduce our energy usage, we can reduce the use of fossil fuels and we can help conserve them for longer amounts of time as we continue to transition to alternative methods. So if we can reduce how much energy we use, then we can help preserve the fossil fuels for longer, which will give us more time to improve technology of renewable sources. We also want to reduce energy usage in order to reduce greenhouse gas emissions. In order to stabilize CO2 concentrations at 550 parts per million after the year 2100, emissions have to be cut in half by then, with further decreases afterward. You will recall that today atmospheric carbon dioxide concentrations are slightly more than 400 parts per million. By 2100, atmospheric CO2 concentrations will be anywhere from 550 to 970 parts per million. They will keep going up, but what we want to do is help reduce how much they go up by. Okay? The best case scenario is that we reduce the increase to just 150 parts per million, basically, during the 21st century. So they reach 550 parts per million in 2100, and then they stabilize. They level off afterward. But if we want to do this, we have to cut greenhouse gas emissions by 50%. And that's quite a change from what's been happening. You will recall that in recent decades, global greenhouse gas emissions have significantly increased. We also want to reduce energy usage to improve air quality. When you burn fossil fuels to make energy for home, for transportation, when you use energy to make products by burning fossil fuels, it releases aerosols and pollution. And if we can reduce energy usage, we will reduce the number of aerosols from coal power plants, from natural gas power plants, from factories, from tailpipes of cars. And that can improve the healthiness. That can improve the health of humans. Reducing energy usage will reduce reliance on foreign oil, including from some countries that may like us, some that may not like us. Finally, perhaps the most beneficial reason to reduce energy usage for you personally in the near term is to save money, right? Save some of those Benjamins. Okay? So, we've been discussing oil, and I just wanted to talk about how the U.S. imports oil and what countries the U.S. imports oil from. So, here we're looking at the top 10 countries we import oil from. And this is as of 2013. And what's interesting is that our largest foreign supplier of oil is Canada, or Canada. 2.57 million barrels per day is imported from Canada. And this is a 33.3%. This is actually responsible for a third of all U.S. oil imports. And the amount of oil we import from our northern neighbor has significantly increased. It's gone up by a factor of 2/3 since 2003. Now, what's very interesting is that a lot of Canada's oil comes from the Middle East. So while we import a lot of oil from Canada now, that's our largest source of oil importation, actually responsible for about nearly twice as much as Saudi Arabia, the second highest source of importing oil. We actually really are indirectly getting oil from the Middle East when we get it from Canada, because Canada gets a lot of their oil from countries in the Middle East like Saudi Arabia, Iraq, Kuwait, and then we get it from Canada. So we don't directly get it from the countries in the Middle East, but we indirectly do. So Saudi Arabia used to be the top importing country to the U.S., still responsible for about 17% of U.S. oil importation. But it's declined since 2003. Third largest oil importer or oil importing country to the U.S. is Mexico, But it's declined. It's been cut in half from 2003 to 2013, basically. We have Venezuela, which produces a lot of good baseball players. Some of the giants in recent years, like Blanco, Scudero, Sandoval, Petit, Hector Sanchez. Okay. And oil importations from Venezuela have decreased as well. But we are starting to get a lot more oil from Colombia, okay, where Shakira is from, right? Muy bonita, or bonita. The amount of oil imported from Colombia has more than doubled from 2003 to 2013. Iraq provides less oil to the U.S. than they used to. Not sure how much of this could be due to the Iraq war that's taken place over this time period. You see some other Middle Eastern countries here on the list. Kuwait, Angola. Okay. So what you do see is in this list, it's filled with several Middle Eastern and also Southern American countries. Okay. And OPEC, the Organization of Petroleum Exporting Countries, is a collection of several Middle Eastern and Southern American or South American countries that import oil to countries like the U.S. But what is interesting is that in recent years, the petroleum consumed in the U.S. that was imported from foreign countries has decreased. In 2013, only about a quarter of U.S. Oil usage was actually derived from imports of oil from foreign countries. And that's the lowest level since 1970. And that's largely a result of increases in oil production for America in recent years. You might have heard of this. In the last year or two, U.S. oil production has reached a 42-year high as we've discovered new drilling techniques. And so this is interesting. Coming back to energy efficiency, we can rank energy efficiency by state. The American Council for Energy Efficient Economy, ACEEE, releases annual reports that rank both state and District of Columbia energy efficiency. And the rankings of the states are based on policies and programs that aim to improve energy efficiency at home, in business, okay, so for both residential and commercial purposes, in industry, factories, and also transportation. And some examples of these policies and programs could be those that require Energy Star appliances to be installed in new homes. Okay, you might have seen, dishwashers or laundry washers and dryers that are Energy Star products. CFL light bulbs in businesses may be required by policies, okay, state policies. There may be state policies that require lower energy manufacturing procedures in factories. There are state policies that require fuel efficiency regulations for automobiles. Now you might be wondering how California ranks compared to the other states in terms of energy efficiency, and it turns out it's one of the highest ranking states. Here are the 2015 state rankings. California is number 2. And you also see that star to the right of the number 2 for California. That means California was among the most improved in energy efficiency from 2014 to 2015. And the states are ranked from, and along with DC, from 1 to 51, 1 being most energy efficient, 51 being least energy efficient. They're ranked by the numbers. They're also ranked by colors. The darker the color, basically, the more energy efficient. And as you go into the lighter colors, the lighter oranges and reds, you're looking at less energy efficient states. Rankings for 2014 were in green, which were kind of made more sense. Not sure why the rankings now are in these red and brown shades, but nonetheless, you can tell the energy efficiency of a ranking of a state. So then you can ask, where are the most energy efficient states located? You see, they tend to be clustered in the Northeast. Okay, Massachusetts, number one, or Taxachusetts. Rhode Island, Connecticut, Vermont. And you see along the West Coast some of the more energy efficient states: California, Oregon, and Washington. You see that some of the least energy efficient states are in the plains, right? North Dakota is lowest on the rankings. Wyoming is second lowest. Okay, you see South Dakota and Kansas are low ranked. Okay, you also see some lower rankings for states in the South. Texas is improving. Texas is one of the most improved states in terms of energy efficiency. You've heard everything is bigger in Texas. Texas actually has more wind turbines and is able to generate more electricity from wind than any other state. And by the way, I'm not showing this to try to criticize any states, right? There's always room for improvement. Perhaps in the future, some of these states in the plains will make big changes to improve energy efficiency. And there's potential for these states. There's a lot of wind potential in the plains, and also solar potential there as well. Okay. But if you're from another state besides California, you might be interested in seeing how that state is, or if you have family in another state, you might be interested in seeing how that state ranks in energy efficiency. Okay. Let's move on to some ideas to reduce residential energy usage. We were talking about reasons to reduce energy usage. Now let's talk about specifically how to save energy at home. And this will really help you for the Green Ninja project. So have a laundry list, no pun intended, of 6 ways to reduce energy usage at home. And you can think of others. If you want some good ones, you can look at the PG&E website. It has a link on your account where you can look at ways to save. But here are some I came up with that may help you. 1, wear layers to use less space heating. Recall that around close to half of all energy consumed by a home in America is for space heating and cooling. Okay? So, and over 40% is just for space heating. So in the wintertime, instead of turning the heater on when it gets cold, you could bundle up. You could put a hoodie on and, you could wear long sleeve pants, maybe thermal underwear, socks. Okay. 2, turn off lights when leaving the room. This sounds very intuitive, right? But it's amazing how people forget, or maybe they don't forget. People are just in the habit of not making a big deal out of it. And so they might leave the room and they just leave the light on, thinking, well, it's just the light, right? And as you saw from an earlier slide, lighting doesn't represent a huge proportion of energy usage in the home, but it definitely adds up, and if you are able to reduce energy usage from a variety of sources in home, you can really put a dent in your total energy usage and save a lot of money. Okay, so every bit helps for sure. This is something that's overlooked, but it can definitely add up. It can also, by the way, help cool your house. Especially if you have some of those old incandescent light bulbs. If you have them on during a hot day, it can actually heat the house up because those incandescent light bulbs generate a lot of heat. Remember how most of the energy they generate is actually heat. Very little is used to throw light. And so the heating will then might have to cause you to turn the air conditioning on longer periods. Speaking of light bulbs, you can switch to environmentally friendly light bulbs, such as the incandescent light bulbs. They'll save you 75% energy. They'll use up to 75% less energy and save you reduce the cost for lighting your home by 75% compared to using all incandescent bulbs, and they'll save you money both on your bill each month and in the long run. They can save you trips to the store. true too, since they last longer. Although nowadays, right, we buy a lot of home goods on Amazon. It's amazing how much what you can buy on Amazon and how fast you can get it shipped. You can unplug the extra refrigerator in the garage. You might have an extra refrigerator in the garage or in a basement that is plugged in, and it might not have much in it, and so it could be using a lot of energy for nothing. And what you can do is just anything that's in there. You might have a pizza or a couple ice creams. Might not have much. We just put it in the regular garage and then unplug the extra refrigerator that's using all that energy. Another way to reduce energy usage at home is substitute an air conditioner with a fan and open windows. Now there are limits to this. If it's really hot during the day, if you live in a really hot place, or a place that gets hot in the summertime in the Bay Area, such as Inland East Bay, Walnut Creek, Concord, or even more so, Antioch, Brentwood, you might really need the AC. Even if you open the window and turn on the fan, especially if you live in an older house or if you live upstairs, it might still get too hot. Or maybe you can handle this in the day. You can just blow the fan and use that. But maybe at nighttime you need air on. Okay, so there are limits to this. But some people find that just opening the windows and using fans, a combination of them, can really help reduce air conditioning, and they might be able to entirely switch during hot days. Some people actually use very little air conditioning. Some people don't even have air conditioner in their homes. Okay. You can allow your clothes to dry outside. So dryers can use a lot of energy to heat up and get the water, moisture out of your clothes. But if it's really hot outside and it's sunny, you can just put your clothes. If you have a yard with a clothesline, you can put the clothes on the line and have them dry naturally and save a lot of energy, right? Now, again, talking about limits. If you live in a unsafe neighborhood, you might not be able to do this. An example, I had a student a couple semesters ago who saw this slide, and she raised her hand and said how she lived in Oakland, and you could not do this in Oakland. She talked about how even if you go to the laundromat in Oakland and you leave your bin, you do your laundry and you have your bin with all your washed and dried clothes. If you leave your bin out even unattended, people will steal it. She said people will steal your shit and they'll walk down the street with your laundry basket. Okay, and I'm just quoting what she said, and so yeah. So just keep in mind that. But if you are in a safe neighborhood, or if you have a garage that gets warm, you might be able to do this. For example, what I've started doing in my home is just put my towels to dry in the garage. Because it turns out the towels take a lot of time to dry. And if you have towels mixed in with smaller items of clothing or thinner items of clothing, like shirts and underwear and shorts, it might take a lot more energy to dry the load, because the towels can weigh down the other materials and take a lot of time and energy to dry. So it might just take the towels out, throw them in the garage, and then the rest of the clothes will quickly dry and use less energy. All right. Mitigation. What is mitigation? It's basically action taken to halt or decrease the environmental impact of a certain action. Okay? And mitigation can include three major components. And we'll be talking more about mitigation in the next, in two of the three next lectures. Not lecture 10, but lecture 11 and 12. Mitigation can include avoiding the impact by not taking a certain action. For example, you avoid the impact of tailpipe emissions from a car by not driving. It could include minimizing the impacts by limiting the degree or magnitude of the action. For example, you help minimize tailpipe emissions from an automobile by not driving as much, okay? Or, not driving as far and walking and biking more. Or rectifying the impact by repairing or restoring the affected environment. So once the environment's been damaged, it's affected, you then try to repair or restore it. So perhaps after the carbon dioxide's emitted, you take it back out of the atmosphere. And there's ways to do this. In the future, in the lecture on mitigation strategies for electric power generation, we'll talk about carbon capture and storage, how we can remove the carbon from the atmosphere. Here is a preview of mitigation strategies for power generation. Here's a wind turbine over water. You have a nice sailboat in the picture. And Denmark is a great example of the potential of wind power. Denmark gets a large percentage of their total electricity production from wind. In 2013, 28% of Denmark's electricity was generated from wind. By 2014, 39% of their electricity was generated from wind. And within the next few years, because of the government programs and policies, half of all of Denmark's electricity will be made from wind. Okay, so that's a great story. By the way, Norway, which is near Denmark, in northern Scandinavia, generates almost all of their electricity from renewable sources. When you think of solar power, you think of solar panels on houses. There's another way to generate electricity from the sun. This is called a solar power tower. It's a working example of renewable energy in use. And what you have here is all these mirrors or reflectors. And they're all angled at this tower. So all these reflectors or mirrors basically what happens is the sunlight bounces off of them, and due to the angle, it gets concentrated, it gets reflected to this tower. So you have all this sunlight being concentrated into this narrow tower, and that generates a lot of heat, which can then be used to turn a turbine to generate electricity. And then this electricity can be transported via power lines to different areas. Okay, it's another way to use the sun's energy to generate electricity. When we talk about renewable energy sources for electricity, we can talk about what percentage of the globe's electricity is generated from renewables. It's about a fifth. Around 20% of all world electricity comes from renewables. And the amount does vary greatly depending on country. For example, Israel generates only 3% of electricity from renewable sources. USA, as we discussed, it's around 13%. But Canada generates nearly 2/3 of their electricity from renewable energy sources. Canada. And then we mentioned Norway, how they generate 97% of their electricity from renewable sources. Okay. By 2030, just 14 years from now, okay, when you are now in your 30s or maybe even your 40s, anywhere from a quarter to half of electricity generation worldwide should be from renewable energy sources. So you see such a large range of tremendous potential for renewable sources for power generation. Okay? In just 14 years, perhaps half of the world's power could be from renewables. Right now, the majority of the world's power comes from fossil fuels. We have such a great opportunity in a short time period to change the way we generate electricity. Okay, it might only be 25%, which is still a quarter, but it's not a whole lot of change from 20%. So you ask what the reason for the range? Well, it depends on what we do in the future. It depends on how the technology improves. Depends on the policies aimed to improve energy efficiency. Depends on funding for renewable programs. It depends on how information is shared between countries, how technology is shared between the rich and the poor countries. Okay. So, hopefully you're getting an understanding of from this lecture about the sources of greenhouse gas emissions, the ways we generate electricity, the importance of renewable sources, the types of renewable sources, the reasons to reduce energy usage, how you can reduce energy usage. And that wraps it up for this lecture.